Hey here, so as usual, I've got a starter, 6 questions. I want you to pause the video, do the starter, and then I'm just about to go over the answers so you can self-mark. So first question, give 2 uses of proteins. First one, you could have growth and tissue repair. Okay, now some people might say building muscle, and you would be correct, but we build muscle through growth and tissue repair, so make sure you say that. And the second one, another use, is involved in the maintenance and regulation of life processes. Okay. Question 2, name the building blocks that make up amino acids. Again, just you need to know this, it's amino acids. What type of reaction is used to make proteins? That is your condensation, and don't forget that proteins are polymers, so you have to say condensation, polymerization. Question 4, name the 2 functional groups found in amino acids. Now the first one is your carboxyl, yeah, that's your COOH, and your other one is your amine one, which is NH2. So you've got a carboxyl and an amine group at either end of the amino acid, yeah, amine, carboxyl. What do we call amino acids that the body can't make? They are essential amino acids. Yeah, where do we get these essential amino acids? We get them from our food. Draw the product. So we've got 2 amino acids reacting together. Remember what I said, the OH of the carboxyl reacts with the H of the amine group, and the carbon and nitrogen linked together. And what you're left with, obviously, because it's a polymer, those 2 react as well, and what you'd be left with is this molecule here. Okay, so that C is bonded to an N. We've made our link, and carries on like so. And remember, because it's a polymer, you want to be getting your N bonds in. Okay, and B, circle the functional group in the protein you just drew and name it. So I'll circle it. The functional group is this here, yeah, the C double bond O NH, and it is called the amide or peptide link. Now it doesn't matter what one you choose, just choose one, write it. Okay? Right. So, lesson 2 of proteins, that is our heading. Now, what we're going to look at first, we're going to look at the types of protein, and there are 2 types. Okay? They are called fibrous and they are called globular. Okay, so we're going to look at each one. We'll look at fibrous first because probably the easiest out of the 2. So, fibrous are proteins that are long and thin. Okay? And they are the major structural material of animals. Okay, humans, dogs, blah 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 blah. Right, what they look like I'm going to draw two parallel lines, kind of off centre, and they go like that. And that is our fibrous protein. That's what it looks like. And just write a wee note here, they can be primary or secondary. And you know the difference between primary and secondary. If, again, we're not talking about alcohols, but in terms of alcohols, primary, the primary alcohol, the hydroxyl group, tends to be, well, it is at the end of the molecule. Secondary alcohol is in the middle. So if we look at this here, the proteins that are at the end, that's your primary proteins, and the ones that are in the middle, yeah, that are attached to two other. So that fibrous protein is attached to one other fibrous protein. That secondary protein is attached to two other proteins. Now that's not a big issue. You're not really going to get asked that. Examples though. Examples of fibrous proteins, you could have muscle tissue, hair, your skin, silk, feathers, and scales. Scales as in fish scales, not brain scales. Okay, so that's what you need to know about fibrous. Globular, a wee bit more complicated. Yeah, structure's very hard to draw. Again, you wouldn't be asked to draw it, so don't worry. Right, so globular proteins are proteins that have spiral chains folded into compact units. Okay, so they have a very complex structure. Yeah, very difficult to draw and to comprehend. So a complex structure. Now, it is these proteins, yeah, the globular proteins, it is these proteins that are involved in the maintenance and regulation of life processes. Okay, and they include enzymes and many hormones. Okay, now I'm going to take my phone because I'm going to really struggle to draw this, but basically that is what a globular protein looks like. Yeah, that's your fibrous, that's your globular protein. It's very, very complex. It's all they're all interwinding, different spiral chains. They're all folding in each other. So if I put this back up here, give me a sec. I'll do my best to draw it, but I can't really draw it that well. So if we call, say that's one spiral chain, and then another spiral chain might sort of go through. Now I can't draw the 3D structure of it, you're just going to have to imagine it. But again, like I said, you're not going to get asked to draw it, so don't worry about that. And the uses, or sorry, not uses, examples of globular proteins. You've got hemoglobin, found in red blood cells. And then, like I said, you have enzymes and you've got some hormones. Okay, so that's our two types, fibrous and globular. Right, next subheading, we are going to look at testing for proteins. Okay, how do we know that we've got a protein? Okay, now I'm going to get a ruler, I'm going to draw this. Now this is an experiment we would do in class, and I'm actually quite thankful that we're not doing it because it absolutely stinks. But anyway, so we're going to draw a side-on test tube. Obviously that would be clamped. Yeah. And here, if we label, I'll label it just now. Right, so that's what you want to have, and if I start labelling this here would be wet pH paper, and it's very important that it's wet, okay, and I'll explain that further on. This here, you'll know, that's the sort of steel wool, the mineral wool that we always put into our boiling tubes, and here is your protein. And we've also mixed it with some soda lime. Okay? So that's the experiment we would have done in class. And this next part, quite important. So, when protein is heated in the presence of soda lime. Now soda lime consists of a mix of calcium hydroxide, okay, which if you did SVSSF would give you the formula that. Okay, so a mix of calcium hydroxide and sodium hydroxide. And again, if you did SVSSF, sodium hydroxide, you would get NOH. So when protein is heated in the presence of soda lime, an unpleasant smelling, complete understatement, yeah, an unpleasant smelling alkaline gas is produced. Okay, now hopefully from that 5 you know what we mean by alkaline. So what happens is we heat up that protein and the soda lime, the gas gets released and it turns wet pH paper blue, okay, and blue for alkalis. So turns moist pH paper blue. Yeah. Now the gases, okay, you've came across one gas. So the gases are amines. Now amines contain NH2 obviously, but the gases are amines or ammonia. Okay, and what's important about that is they both contain nitrogen. Yeah, and the reason they both contain nitrogen is because obviously the protein contains nitrogen, so when we're burning it, the nitrogen's coming off. Right, now, just a wee side note, I did say it's important that we use wet paper towel, wet pH paper. So, wee side note from that 5, again, this is one of the last things that we did. I don't know if you can remember the experiment with the ammonia fountain, but ammonia dissolves in water to form an alkali. Yeah. Okay. Right. I'm just going to take a new sheet of paper and we're going to start looking at enzymes. Okay. Now, if you do biology, whether higher human or just normal higher, you'll feel very at home here. So we'll go through it. Now, enzymes, what you need to know about enzymes are globular. Okay, so they're globular proteins that are, and this is important, okay, are biological catalysts. Now you can't just say enzymes are catalysts, you need to say they are biological catalysts. Okay, so enzymes are biological catalysts. Now the next part, again, you'll have known this from that 5 chemistry, but each catalyst is specific to a particular reaction. Okay, so that means there's only one catalyst for one type of reaction, there's another catalyst for a different type of reaction. Yeah, each catalyst has one specific reaction that it works on. Okay, so example, the enzyme pepsin only catalyzes the hydrolysis of proteins. Yeah, we couldn't use pepsin for something else, and it's all to do with the sort of the shape of the enzyme or the active site, but we'll get onto that. Now, next part, so enzymes contain a region called the active site. Okay, and the shape of this active site allows specific reactants. Now, instead of saying reactants, I'm going to change this into a new word. Again, if you've done biology, you will have probably came across it. Substrates. Okay, so enzymes contain a region called the active site, and the shape of this active site allows specific substrates to attach like a lock and key. Now, I am aware that in biology, instead of saying maybe lock and key, you might use the term induced fit. I'm not going into that in chemistry. I don't have to. So if you do take biology, don't be screaming at me. Just relax. So next part, again, quite important. Not all substrates fit into this shape. Okay, so not all substrates fit into this shape and react. And that sort of brings it back up to the very top here. So not all substrates fit into the shape and react, and that's because the catalyst, well, the enzyme, sorry, I should maybe really, oh, no, it doesn't matter. In fact, I will, each enzyme or each biological catalyst is specific to a particular reaction. Okay, so not all substrates fit into this shape and react. And also, enzyme function is related to the shape of the protein. Okay? So, it's easier, obviously it's easier to show you what's happening with pictures. So I'm going to show you an example of what we mean by pretty much what I've just written, okay? So I'll use a different pen. What we have now, look carefully to how I'm drawing this, okay? And you notice there's different shapes. That one kind of looks like a cup, wee triangle, and like a square, okay? So if we call that our enzyme, okay, and I should point out that's your active site. You've got an active site there, and there, okay? So the active site's essentially these wee shapes. But again, that's not as important here. And if I draw this, now obviously my drawing's not perfect, so you're going to have to use your imagination a wee bit. If we call that our substrate, okay, hopefully you can see that this substrate can fit into the enzyme, okay? And what happens, we are left with a situation where it goes like this. Again, just, it's not the best of drawings, but it will do the job. And the substrate fits nicely into the enzyme. Now this is where you get the whole, what I was saying earlier, the whole induced fit where the enzyme sort of snugs in, but don't, like I said, do not worry about that in chemistry. Now, obviously once the substrate's in there, the reaction can take place and you can get that sort of snapping off here, okay? So we're essentially showing off a hydrolysis, so we've got a large molecule and we're breaking it down into two smaller molecules. And if I just carry this on, again, this is the cool part because you'll notice when the substrate leaves, the enzyme is exactly the way that it was at the start, okay? And that sort of brings back what you learned in second and third year. Enzymes don't get used up, okay? So you'll get one product, okay? So that is product 1, and that is your product 2. Okay. Again, enzyme not getting used up. Now, I keep using this word specific, yeah, and the enzymes are specific based on the sort of shape of the active site. So, what we mean that enzyme is specific to that substrate. However, if we use this enzyme, and we try to use this substrate, okay, so substrate and enzyme, okay, hopefully you can see that that substrate can't fit in to the enzyme, okay, the lock and key essentially, so substrate does not fit. Okay, so this isn't specific to this substrate. And that's it. That's all you really need to know about the lock and key mechanism. Okay, so very much like how my house key would open my house, well, my front door only. Enzymes are pretty much the same. Okay, you've got one enzyme for one reaction. Right. Next one we're going to look at, okay, is optimum temperature and pH. And again, if you've taken biology, you'll be right at home here. If you haven't, don't worry. So, optimum, okay, and this is important. Biology will tell you the same. So, optimum in the case of enzymes, optimum means when the enzyme is most active. Okay, so I'm going to highlight that. So optimum is when the enzyme is most active. Now, usually what a lot of folks say, if you are working at optimum, it's working best at. Now, you can't say that, okay? So do not say works best at. Okay, when you're talking about optimum, you're talking about when the enzyme is most active. Yeah, most active. Right. Next one we want to look at is rate of reaction. Okay. So normally, yeah, in a typical everyday reaction, normally as the temperature increases, what happens to the rate? Yeah, so normally as the temperature increases, the rate also increases, and that's what we told you in second year, third year, fourth year, and even the start of this year. Yeah, normally as the temperature increases, the rate also increases. We went into a wee bit more detail higher, and this is due to molecules containing kinetic energy, yeah, EK, equal to or greater than the activation energy, okay, which is EA. Again, you need to know that from Unit 1, but that's normally what happens. And if I draw if I draw a diagram with temperature on the bottom, rate, again you can put units in I suppose per second for rate, remember, degrees Celsius for temperature. So as we increase the temperature, the rate should go up and it should look like that. Yeah. Now, what you need to do, what's important, is you need to be able to recognise that graph, because it can come up, usually like a wee multiple choice question, but be able to recognise that graph. Okay, it's exponential. It goes like that. However, yeah. However, with enzymes, what happens, they're a wee bit different. So reactions involving enzymes. So however, with enzymes, after a certain temperature, okay, and we'll call it the optimum temperature. So after the temperature where the enzyme's most active, what happens is the enzyme becomes denatured. I've completely spelled that wrong. It becomes denatured. Now I'm going to highlight that because that is so important. Again, I'll explain what I mean by denatured in a wee while. So after the optimum temperature, any temperatures that are higher than that, the enzyme starts to becomes denatured and no longer works. Yeah. So what we mean by that is the active site is permanently damaged. And because it's permanently damaged, unfortunately, we can't reverse it. Okay? We can't reverse it. The minute that active site's been damaged, game over, we can't use the enzyme anymore, so we would need to chuck it and we would need to get a new one in. Okay? Right, we're almost there, we're almost finished. So, reactions involving enzymes. The graph looks a wee bit more, a wee bit different. Okay, so it's still that, we've still got temperature on the x-axis and rate on the y, and instead, obviously in a normal reaction, as we increase the rate, as we increase the temperature, the rate gets higher. But with enzymes, what happens is the rate gets higher until it reaches what we call the optimum temperature, so where the enzyme is most active, and then at this point, it begins to denature and it stops working, and because it stops working, the rate starts to go back down. Okay, so at this point here, this temperature, that's your optimum temperature. The minute we get above that point, the enzyme starts to denature and it's game over. Once it's denatured, we can't reverse it. Yeah, we can't go back to our optimum temperature. It wouldn't work anymore. Okay, so temperature. So temperatures. So temperature above here, and I'm going to point. I'll make a wee note here. So Yeah, so temperatures above here cause the enzyme to denature. Okay, and then in the next lesson, I'm going to talk about what actually happens. I know I said that the active site sort of is damaged, changes shape, but I'm going to look at it from a chemistry point of view, okay, and it will bring in hydrogen bonding again, but we'll leave that for the next lesson. Okay, so temperatures above here cause the enzyme to denature. Now, pH is exactly the same. Yeah? So again, you've got rate and you have pH. Okay, so you remember the range of the pH scale, 1 to 14. Any above 7, alkalis, any below 7, acidic. Acids, and anything pH 7, they are neutral. Now, what happens, again, exactly the same sort of shape. And here is the optimum pH. Now, what's important about the optimum pH? Now, usually a lot of people think, oh, optimum pH must be 7. That's not the case. It depends on the reaction. Some reactions prefer alkaline conditions. Other reactions prefer acidic conditions. Okay? So, what's important is that the optimum pH does not have to be 7. Yeah? Some reactions prefer alkaline or acidic conditions. Okay, and last wee bit here. This is where it's different from temperature. Okay, they show the same curve, the whole up and down, but the difference between pH and temperature is that the enzyme only becomes denatured when you get to a temperature after the optimum temperature. These temperatures here, yeah, we could heat it up to optimum, cool it back down, heat it up, cool it back down, and we could keep on using the enzyme as many times as we want. It's only until after this optimum temperature does the enzyme become denatured. However, pH is different. If you are in a pH below or above the optimum pH, it becomes denatured. Okay, so pH is below, okay, and above the optimum pH will denature the enzyme. Okay? Now, just to sort of show you what I mean by denaturing, okay, I'm going to go into more detail. Like I said, I'll start looking at telling you about hydrogen bonds, stuff like that. But on a simple sort of term, if we have okay, say we've just got an enzyme there. Now say we've got a high temperature, okay, so it goes through denaturing, it becomes denatured. What happens, like I said, the active site sort of changes shape, becomes damaged, and again, not the best drawings, but hopefully it sort of gives you an idea. Active site becomes damaged, and permanently as well, okay? We can't reverse that. Once that shape's damaged, think of if you heated a bit of plastic, once it starts to melt and change shape, you're not going to get it back perfect, okay? So, active site has became permanently damaged. Okay. So that's us, but we're just going to quickly recap everything that we've done. Okay. So, right at the start of the lesson, you learned about two types of protein. You learned about fibrous and globular. You need to know the difference between the two. So, fibrous, simple proteins, major structural material of animals, long and thin, can be primary or secondary. Different examples, you've got muscle tissue, hair, skin, silk, feathers and scales. Globular, they're a wee bit more complex, spiral chains folded into compact units. And the examples, you've got hemoglobin and red blood cells, enzymes and hormones. What I do want to add here, they are tertiary, okay, and quaternary. Okay, now we haven't went past tertiary, don't worry about quaternary, but yeah, just as a wee sort of side note, they can be tertiary or quaternary. Testing for proteins, we can burn it in the presence of soda lime. That will give you like an alkaline gas, either amines or ammonia. And what's important to test for it is that these gases will turn moist pH paper blue, and it has to be moist in order for the ammonia or the amine to dissolve into the water. Okay. Next part, we spent quite a bit of time on enzymes. They are globular proteins and they are biological catalysts. Make sure you know that, biological catalysts. Each enzyme is specific to a particular reaction, so each one enzyme works for one reaction and that's it. Okay, then you get another enzyme that works for another reaction and so on and so on. And that's because they've got this lock and key mechanism. Okay, all enzymes contain your sort of active site. Yeah, and that allows the substrate to fit in, hence the term lock and key. Okay, you can break up, hydrolyze molecules, and what's important also is that the enzyme doesn't change. Yeah, remains the same. Specific in that you have to have the right sort of shape. Yeah, the enzyme has to have the correct active site, essentially, otherwise the substrate won't fit. Next thing we spoke about optimum temperature and pH. It is important. In the case of enzymes, we're not talking about the optimum, like where it works best at. We're talking about the enzyme being most active. That's where it's most active. Rate of reaction, you need to be able to recognise that. Yeah, as we increase the temperature, the rate of reaction increases, and it's due obviously to molecules now containing kinetic energy greater than or equal to the activation energy. Enzymes are a wee bit different. Okay, after we reach temperatures above the optimum, the enzyme becomes denatured, no longer works, and you're going to get a lower rate. Okay, the active site is permanently damaged. We're not going to be able to reverse that. So this is what happens here. Yeah, the rate goes up to the optimum temperature where the enzyme is most active, and then any temperature above that optimum, it denatures it. Okay, once we're in this point, it's game over. Yeah, we can't go back. Think of a ball going down a hill. The minute you sort of knock that ball over, it's just going to keep falling. Yeah. pH, identical to enzymes. The only difference between temperature. The only difference between pH and temperature is that pH will denature the enzyme whether it's below or above the optimum pH. Okay, and that's just what we mean by denaturing. But again, I'll go into more detail about the hydrogen bonds next lesson. Okay, so that's us. Thank you.